engineering. Okay. Let's say those who are technologically challenged. We are. Oh, yeah. So we actually, if you like it and you think it would be useful, talk to the other faculty and ask them if they're willing to do it. If they are, we have the tablets, and it takes me about an hour to teach someone sort of how to do it. It then takes them about another quarter to sort of work out their own bugs and get. Most of the stuff that makes this work is not hard. It's doing weird things like making sure the extended desktop works with your Bluetooth pairs and things like that. There's a lot of little sort of annoying small steps that really tend to bother you.
So are you the designated person game, or you just do it on your own?
I actually wrote a small grant to do this, and started it because I thought there are. The legacy is at graduate school at Stanford, they record the classes, but they have actually auditoriums that are set up with pan, zoom, tilt cameras in multiple places. They've got microphones built into the back of every seat so that when you ask a question, it gets recorded as well. Well, actually, that's the hardest part, as it turns out. Not just the sound, but recording my voice is easy. Recording your voice is actually quite hard. And so one of the things we've been looking at is there's a couple of companies that make devices that use some fairly interesting signal processing with an array of microphones that can actually figure out who's talking and home in on them and basically form a beam and steer it. It's actually...
We can just hand Eric a microphone.
Because Eric is not the only one doing it. It turns out that, by the way, that beamforming stuff, if any of you... Here's a plug for my other class. If you want to learn how to do estimation... a lot of that would where the linear estimation would come in, the beamforming thing. It's actually a derivative of a technology that they're currently developing to locate snipers. So what they've got is essentially what looks like a ball with a whole bunch of microphones stuck on the outside of it, and it sits on a pole on top of a Humvee. And as a bullet goes flying by, on the outside, it doesn't actually have to hit the Humvee or even come that close to it. It actually detects the sound from all the different ones which are located in different areas, and it basically detects the velocity, from which they can back out what caliber gun it was, and they actually figure out where it impacts, where the velocity trail. They reverse it and run it back, and they said, your target is on this line. As they move, if they ever fire again, it says your target is right here. All right, and that's it takes essentially 2 shots to locate them completely. What's that? Apparently, the problem is not getting shot at. Apparently, it does happen on their own, but the idea is to sort of locate. By the way, they do this with artillery as well. So when an artillery shell is fired, they take 3 measurements with a radar as it's rising, and they actually compute the point of departure before it's even reached apogee. So before it's even gone to the top and started coming down, they fire a shell in return to hit the guy that's on the other side. And which is why they do something called shoot and scoot. So they basically set up, fire a mortar off and they run, pack it up and they run because they know there's a shell coming in the other way. All right, and they just try to get out of the way as fast as possible. Anyway. So the recording technology is a little bit more benign, but yes, Shell.
When you return a fire, doesn't that mean that someone can return a fire to you? So doesn't it like?
It depends on the scenario, but yes, there's a reason. So what you will see in the military's arsenal is something that looks like a weird form of tank with a really, really long gun that sort of starts at the back and sticks way out in front, and that's mobile artillery. So they actually can move very fast. They move, elevate, fire, put down, move. They spend, probably 50 seconds in one spot before they, less than a minute between, and half of that is aiming. So the other thing they're doing now is they're actually getting it to the point where they can actually, currently most of the projectiles from artillery are dumb in that they are not guided whatsoever. And now they've got, a lot of people have been working on making GPS that can withstand the 20,000 Gs that comes out of the muzzle when you fire it. And the idea is that it then locks on as it's going up, and then on its rise you say, oh, where would you like me to go, by the way? Because, I'm rising and I've got lots of cross range I can hit right now. So if you want me to go that way, just tell me where you are, but you've got 4 seconds before I can't do anything anymore. And they will actually sort of turn and steer and do that. Then they actually they aim kind of roughly. Sort of. They use a base bleed, as I understand it. They use a base bleed to get longer range. So they've basically got a liquid in the back of the thing, and they actually leak it out very slowly, and it forms essentially a liquid cone at the back that reduces their drag, and that gets them much farther downrange. And they can sort of modulate how much they let out. So basically, they can alter their pitch by drag that way, and then as I understand it, they've got little fins that sort of pop out, and it's pretty small actuation, little tiny fins that sort of pop out for a brief amount of time and shut back down. And this whole thing is rifled, so it's spinning very fast. And so the idea is that you actually only need 2 fins, and if you modulate them correctly,
you only need one.
You only need one? They only do it with one?
The control problem is so challenging because it's rotating.
Right.
To rotate, you need to get one fin out from one position.
Right.
Rotate it and then get it out, get it in, rotate it 90 degrees. And
get it back out, get it back in. And they do it with one fin? Okay. So so you've even got one fin that they do. I believe they use pneumatic actuators, right?
Yeah.
And they could probably use piezoelectrics too. They're very small. It doesn't take much when you're flying at 5 times the speed of sound, right? You're moving very fast. So you've got huge dynamic pressure, which means a little tiny burble is enough to do it. So that's the thing. And on the other side of this, of course, they're now sort of figuring out that they can actually, if they can track it with radar, they can track it with a laser. If you can heat up the skin enough, if it's got an explosive charge, you can actually detonate it in the air before it goes up. Everybody knows what the problem with this is, of course, right? What happens when you detonate something in flight? What still lands at the intended destination? The center of mass, right? So all you've done is created a single point clump to now a large scattering of little clumps coming down. If you can destroy it into little tiny enough clumps, then the air drag slows them down, and they're not lethal. So that's the whole idea. Anyway, enough of that. So, before we go on, I guess the big question is, are there any questions? Anyway, all this stuff is perfectly clear to you. Huh? Well, if it isn't, ask me questions. This is how I know. Yeah?
Sort of a generic question. It seems like they use Laplace transforms for mechanics and Fourier for signals. Is that generally right?
No. The reason people use Fourier transforms, so here is the complex plane. So here we've got the reals, and here we've got the j omega axis. All right, so all of this is the Laplace domain. Okay, whereas only this axis is the Fourier transform. Now, the Fourier transform is very related to a Bode analysis, okay, which we'll get to. It's a frequency domain analysis, where you are not concerned with the transient specification. You don't care how fast your rise time is. You don't care how much overshoot you got. What you want to know is, I stick a sine wave in, I'm going to get a sine wave out. That's linear. If I stick a sine wave in, I get a sine wave out. The amplitude is going to be changed, and there's going to be a phase lag. I want to know what those two are doing, what the amplitude and the phase lag is doing as I stick a continuous sine wave in. All right, so this is more of a tracking response as opposed to a transient response. So what this class is going to do is we're going to sort of bifurcate into 2 directions. Once you get sort of the basic mechanics of how to take a differential equation, convert it into a transfer function, we then split into 2 directions. On the one direction, we're going to go with root locus, and root locus is fantastic for doing transient response. How much overshoot, how fast it rises, is it damped, is it undamped, things like that. So if I put a step input in, how's it going to respond? Or if I put an impulse in, how's it going to respond? All right, this is really good for regulation. All right. On the other hand, we're going to go to the frequency domain, which is the Bode response, which stays basically on the j omega axis, which is you're looking for a continuous signal in versus a continuous signal out. You're not actually worried about the transients in between. Okay. The idea being that on anything you're going to measure anyway, the transients have enough time to die out, as long as you haven't pushed the thing unstable. All right. So when you're, for instance, buying an amp from for your stereo, what you are looking at is not the transient response. You don't really care how it responds to a step input. What you care is, I'm going to put my frequency in, how much distortion is there? which is, by the way, a phase lag argument. How much amplitude gain or reduction is there? Things like that. So these are things like total harmonic distortion, things like that. So that is concerned only with the steady state response, not necessarily to the transient that you get. And so they're two sort of different worlds. All right, one is frequency, one is transient, and they cross over. There's a lot of crossover between the two. So they aren't completely separate, but at the same time, the reason that people use mostly in the signals and systems domain, people use just the Fourier transform and the j omega axis is because they're only concerned with the steady state. They aren't concerned with the transient performance, because generally if you're doing in electronic circuits, the transient is pretty damn fast. And so, unless you're pumping in, and you can get from the frequency analysis where the system is going to start to break down, at what frequency it starts to roll off, and where you start to get problems. Now, by the way, that, of course, all assumes that it's linear. When it's nonlinear, you get wonderful things like hysteresis in the frequency domain. So you get a different response increasing in frequency than you do decreasing in frequency. All kinds of, nice, really unusual stuff. And if you're into that stuff, I would suggest you take Jorge's nonlinear controls class, which is, a little bit more mathematical than this one. Just a tidbit, but interesting nonetheless. All right. Any other questions? Dead silence. All right. Guess you guys are bored. All right. So let me. So let's see. Let's catch up to where we were last time, which is what we did was we basically take. Let's start from here for a real quick catch up. So we know now how to take our equations of motion written as generic Laplace transforms. So we can take our equations of motion, write them as differential equations. We take Laplace of the whole equation. We know now to take a ddt, substitute for an s, remember the initial conditions. I know you guys are going to forget it because we always do it from zero initial conditions, but they're there. Slam it all through, do a little algebra, and rearrange this to some form of ratio of polynomials, which can be rewritten in the form of a gain times a product of zeros in the numerator and a product of poles in the denominator. And let me get the right. Yes, okay. So with that, we can always take this whole thing and rewrite this as coefficients on top of the poles altogether and rewrite them down. And from these, we know what the responses look like. So these are the modes of the system. And from the modes, I extract the building blocks which the time domain response will be assembled from. Okay? What that says is the modes of the system, the things that appear in the denominator, or in what is called the characteristic equation, which is just set the denominator equal to 0, all right, are going to be the individual building blocks from which I can build up my response. What the numerator is going to tell me is how much of each of those go in. All right, it's going to tell me how much my mixing coefficients, if you will. So think of this as, I'm making bread or something like that. And so, what I've got is, how much yeast, how much flour, how much water, whatever else goes into bread, since I'm not that good of a bread maker. But yeast, water, flour, I think those are the basics, right? And then the question is, how much of each? How much of each of your recipe components is given to you by the numerator? Which components you've got is given to you by your denominator. All right, so when we've got, so the c's in the numerator are called the residues, and they are constant, at least for a linear system. And basically, when we've got real non-repeated roots, I can use the cover-up method, and the cover-up method is just to take the pole and multiply it, so s minus that pole, times your transfer function, evaluated at that pole, which will isolate that coefficient. And you can do this for any real non-repeated roots. Okay, so we've done real non-repeated roots. Here was a typical example that we did, and what you can see is from the denominator, I extract that there's going to be a step response, an e to the minus t response, and an e to the minus 3t response. It's going to be some mixture of those, and then using the cover-up method, I come up with the coefficients for each, how much of each I've got. And so, for instance, I've got a lot of the step. I've got a negative amount of the e to the minus t, and I've got a much smaller negative amount of e to the 3t. All right, so this is sort of where the mixture comes in. All right, now when we do the complex roots, as we said, they always come in complex conjugate pairs. The reason they come in complex conjugate pairs is because the coefficients of your differential equation are real. The reason the coefficients are real is because they are real physical values. They're spring constants, capacitors, inductance, all of those values are real. Okay? So we can rewrite these in a number of different ways. We could write this as s squared minus 2 sigma s plus sigma squared plus omega squared. And we can actually break this up into we can factor this into two complex poles. It works, as it turns out. If you do this, what you wind up with is you wind up with a complex C1 on top of it using the cover-up method. And if you actually go through and you work it out, you'll find that C2, that goes with the complex conjugate root, is the complex conjugate of C1. And when you sort of do all your cross multiplication, you get back to reals once again. So given this, you can go ahead and reassemble so using a definition for C1 of A plus JB and C2 of A minus JB corresponding to the sigma plus or minus J omega, okay, using those guys, we wind up reconstructing these and we get two pieces out of the tables, so number 19 and number 20. And when we do this, we wind up with a total response that looks like 2 times the magnitude of C1, and the magnitude of this, right, is the square root of A squared plus B squared, e to the minus sigma t times the cosine of omega t plus the angle of C1. All right. So what this tells you is it gives you a formula that all I have to ever do is find one of them, and I'm done. Because I know that for the two of them together, I'm going to get an amplitude that is the magnitude of the complex coefficient, and then a phase lag associated with it. And it's always going to come in this form. And what that looks like when we plotted it is we've got an e to the minus t envelope that goes on the outside, and then we've got a cosine omega t plus phi. Well, depending on what phi is, that's going to either take me all the way to starting at 0, in which case it would be a sine, that would be a minus 90, or I could start at 1, in which case it would be a cosine, and it would be 0. Okay. So that was where we were. Any questions up to there at all, whatsoever? Somebody make my day? No? Okay. I'm telling you, you will learn. What's that? Eric isn't here. Well, that's okay. He's the only one who sort of, I have to keep quiet.
Can you go back to the last slide just for a second? Yeah.
Yeah.
No question.
No question, you just wanted to write. All right. Okay. So the interesting thing is, even without calculating the residues, just by essentially factoring the denominator, I now get to see what the response looks like. All right, and factoring a polynomial is really easy. Okay, especially now in MATLAB, it's one line. All right, it's truly a little note about MATLAB. Okay, MATLAB is a wonderful tool. All right, it really is. It's a great tool. You get to do wonderful things with it, but it's also a hideous crutch. All right, which is it's such a powerful tool that you wind up, it is. How can I put this gently? Emasculating. All right, in that you lose your entire ability to do this by yourself. You become dependent on it really quick. It's the heroin of the engineering world. All right, they sort of give you a little taste for cheap when you're a student. They're like, sure, have the student version. It's only $50. What is it? 100 now? Yeah. They're like, have the student version. So most places have site licenses for MATLAB at academic places, and then you get hooked, and then that's it. Then you can't do anything without it. I mean, it's an evil thing, but it's also a wonderful thing. So you sort of just remember that. You should be able to do most of this stuff without resorting to MATLAB, and understand that MATLAB just makes it much easier and faster. Okay, but you can do it. So, and you guys somewhere way back in sort of the primordial recesses of your neurons remember how to factor polynomial equations. All right, even thirds and fifths and fourths, that can be done. They're iterative methods that work really well. Anyway, okay. So one of the things to remember here is. Why is this down? Okay. So, from your ODE class, if you can remember that far back, you had to do a huge amount of work to figure out what y of t looks like. I mean, you had to do a tremendous amount of work. There was a very, very small class of inputs for which you could actually even find it analytically. The deep, dark secret of differential equations is outside of ordinary linear differential ones. There's like 217 that have been solved. Every one of them is named. And, if you are sort of lucky enough to solve another one, you get it named after you. But all the easy ones have been done. And, there's sort of these really obscure hard forms that, nobody quite gets. And, the truth is, everyone just does it numerically now. Yeah?
Was that on the previous slide? Sorry to go back. How did you go from the sine plus cosine to the next one?
Oh, from sine plus cosine to cosine plus an offset. That would be a trigonometric identity. Okay. That, sine omega plus cosine omega, as long as they're at the same frequency with different mixture coefficients, wind up being a cosine with an offset or a sine with an offset phase. It's a simple trig identity. And it's probably not in this book, but if you look it up in the mathematical tables book, you will find it. No problem. Okay. So the joy is that now the solution is almost trivial. Not quite trivial, but almost trivial. All right. Basically, I hand you, I don't care how many complicated differential equations. In the homework, I think we gave you 3 coupled differential equations on the first problem. It looks kind of hairy, but it's not that bad. And the truth is, you whip it into the Laplace domain, substitute, solve algebraically, and you're done. And that's 3 coupled differential equations, which is pretty nasty. It's going to wind up being a 5th order system, by the way, and you can solve for it. So here's another example. I'm going to take y of s is going to be 5s squared plus 16s plus 62 divided by s plus 2 and s squared plus 2s plus 10. Okay? And I'm going to say, cool. So I'm now going to say, not a problem. Let me see what this solution looks like. Right now I know that my solution is going to look like, without even literally by inspection, it's going to be some coefficient e to the minus 2t plus, and these guys, by the way, this is if I factor this one, I should get quadratic formula. Works quite well here. S is equal to minus 1 plus or minus 3j.
Yeah, what you're doing is you're just parsing it in your head, right?
Yeah, I'm looking at this,
Yeah.
and I say, okay, this is going to be some a, I don't know the coefficient of it yet,
Right.
but I know that that's an e to the minus 2t, and I know that this guy is going to be b e to the minus t times cosine 3t plus some offset. All right, and these 3 things, a, b, and c, are functions in the numerator.
And you see that just by looking at it.
You see that just by looking at it.
I see it.
Yes. Okay? You see this s plus 2, that's an e to the minus t.
Yeah.
Immediately. You see this s squared plus 2s plus 10, and you factored it to minus 1 plus or minus 3j, and you say, oh, well, that's easy. That's the sigma. That's the e to the minus t. And I know that it's going to be a cosine 3t, there's the omega, right? 3t plus some offset c. So the numerator is simply going to tell me what b is, what a, b, and c are.
What would sine look like?
Same.
Well, no, I mean, if
Sine means that c is 90 degrees.
Okay.
That's it.
Okay.
There is sine and cosine are identical when you have a phase lag.
Okay.
Right? It's just which phase lag you, yeah. Right, because they're 90 degrees out of phase with each other. So, yeah. Ever. No. Just write it as 1. Right? In fact, I already know this, and now I'm going to say, okay, well, since I know how to factor this, I can go ahead and use the cover-up method. All right? So if I do s minus 2 times y of s evaluated s equals 2, sorry, s plus 2. And I evaluated this s equals minus 2. Yep. Right, so I'm going to do this, I'm going to say, okay, so s equals minus 2, that's 5 times 4, 20, minus 32, right? That's negative 12 plus 62. That's going to be 50 on the numerator. And on the denominator, I'm going to have 4 minus 4 plus 10, 10. So there's A. Now how hard was that? That was really hard, right? Oh, that was so hard. That was so hard I can't give it to you on an exam. All right. Now, the more interesting one is to do the cover-up method with writing it down as minus 1 plus or minus 3j. And that one I will let you guys do yourself, but I will give you the answer. Right? Because you can rewrite this. You can rewrite y of s is equal to 5s squared plus 16s plus 62 all over, I've got s plus 2 times s minus, let's see, s plus 1 plus or minus 3j. Right? So there's actually 2 of them in there. Right? And I can do the same thing, so I can actually do, to get C1, I'm actually going to do s plus 1 plus 3j times y of s evaluated s equals minus 1 minus 3j. Okay? And I'm going to slam that through, and it's nasty, right? And you're going to have to multiply by the complex conjugate in the numerator and denominator to get it. And eventually, you're going to do a little bit of work to do so. You wind up that C1 is equal to minus j. All right? Therefore, I immediately know that C2 equals what? Plus j, thank you. Okay? And then that means that the magnitude of C1 is equal to, what's that? 1, right? Therefore, I know that the formula, if I go all the way back to here, right, I know that this is 2 times the magnitude of C1. Therefore, B is equal to, I have it as 1 as opposed to 2. No. I have it as 1 in my notes. So you guys may have to work that one out for yourselves to sort of verify it. All right. So if the magnitude of C1 is 1, all right, I actually think that should be 2. What's that? No. The magnitude of C1 is 1, but if you look at the response of the total system, you've got
if you go back to the formula, you can divide everything by 2, and you can get rid of both 2's. That's why you have 5 and 1 instead of 10 and 2.
Got it. Okay. I accept that. What was that? So if I go back to the original, this one, right, and I can divide through the whole thing, actually, sorry, go back all the way to this one right here, I can actually factor the 2 out.
So you read the 2 out front.
Right? So there's a 2 out front, and then I'm just looking at what I've got in between, and so I can just pull that out. All right, that would be the thing I'm looking at. Although I'm not.
No, you go back to the red equation.
This one right here.
Yeah, that.
Yeah.
You can divide by 2.
I can divide by 2, yes.
And you get rid of 2a just to get a, and you get rid of b.
Right, but I still have a 2 in there.
Where's that 2?
I still have to find a place for this 2.
Still says you got 2 times the result.
What you're saying would be 1/2 y.
Okay.
Right, but you would have a half y of t. So I'm actually this comes from using this guy right here, an a plus jb on either side, and putting it together.
Where did this 2 come from anyway? And why is that?
This 2 comes from when you cross multiply everything together. Back up here. All right. So I'm going to stick with my 2 because I think that's that is the right one.
So B is 2C1?
So right, so B would be 2C1, 2 times the magnitude of C1.
Right.
So B would be 2. And this is a place where you guys can actually check it, since it's an easy enough thing to simulate and isolate the response to it. And in fact, you can actually do the residues in MATLAB by typing the word residue. So it will do it for you. So from this one, we get that B equals, so I'll have to check on that one and get back to you, but I think B is going to be equal to 2, and then C is going to be equal to, in this case, minus 90 degrees, right? Because the angle of this is
Not plus.
plus or minus, doesn't really matter.
Okay.
It makes absolutely no difference, right? And in fact, if I really want to write that then down, I have so y of t, right, is going to equal to right here we have 5 e to the minus 2t plus, and we've got a 2 or a 1, and then it's just actually going to be a sine 3t because cosine plus 90 degrees is sine, or cosine minus 90 degrees, still sine.
So the reason you wrote it as minus 90 is because we went counterclockwise? Just
Yeah.
As a convention?
Yeah.
Okay.
That's always how you, this is generally the way you go around. So that would be 90 degrees. For the, if I went with the, actually with the minus j, I'm actually going minus 90 degrees, right? So, and I can just write this, or I can write this as the other way, which is just cosine of 3t minus 90. All right, and there's my solution.
Going clockwise. We're actually going clockwise with the minus j.
We're using C1, which is minus j,
Right.
and so minus j is here, so this is,
Okay.
that's minus 90 degrees.
Okay.
Yeah.
I'm not clear on how we arrived at negative j for C1.
So what we did was we took s plus 1 plus 3j times this thing, y of s, and then evaluated it for s equals minus 1 minus 3j.
And is that the numerator or the denominator?
Both. Everywhere you see an s, you're going to replace it. The one that would be s plus 1 plus 3j would go to 0.
So it's a big mess and it just all falls out to negative j.
Yeah, so basically you're going to wind up with a complex expression in the numerator and denominator. And once you do all the algebra, then you multiply the top and bottom by the complex conjugate, in order to, which is just 1, right, which you're allowed to do at any time, which is going to turn it into a slightly nicer form.
Okay.
Mariano's doing it right now to verify whether it's a 2 or not.
And then the denominator on y of s, s plus 1 plus or minus 3j.
Yeah, this is 2 terms, right? This is s plus 1 plus 3j and s plus 1 minus 3j. So this one is going to cancel with that one. And so all you're going to be left is the s plus 2, the s plus 1 minus 3j when you're evaluating s plus 1, and that's going to be real, right?
Did you factor the term that was originally there?
Yes.
Okay.
Yeah. So these are just the 2 roots, right? So I can always write, s squared as, s plus the root squared.
Okay.
Right?
In the term you got, the 2 cosines,
Yeah.
whenever you have a complex pair, you can use either one of the solutions or just use its magnitude and its phase?
Correct. It's always going to come out plus or minus the phase. And plus or minus the phase off of cosine is the same towards the sine. So it doesn't make a difference.
Oh, and their magnitudes will always be the same.
Correct. Magnitude's always the same, and the phase is going to be plus or minus depending which one you use, but it doesn't matter because off of cosine, when you take the peak around, it doesn't matter whether you're going plus or minus that phase. It has the same effect. All right? So it makes absolutely no difference. And the jury, is the jury in yet, Mariano? Is the jury in yet? Okay. We'll table that one for when we go. Okay. So far, where have we gone with this? We've gotten, basically, we have the inverse Laplace transform down, and the partial fraction expansion. So between these two, now so far we've done non-repeated real roots, and we've done complex conjugate pairs. All right? Now, this is always, by the way, going to come up in the form. One of the tricks I can do is I will always have one less s in the numerator as in the denominator when I break it up into partial fractions. So one of the ways to do it, for instance, is I get this C1 over s minus P1, right? And then for the complex conjugate, I can always do AS plus B all over s squared plus, or let's do the s minus sigma squared plus omega squared. All right? I can always rewrite it in this term, in this form. Right? And then just do, now C1 is really easy to find. To get these guys, I can do the cross multiplication and match the remaining coefficients. All right? And I've got C1, so that's an easy one. Okay, so, and if it's an s cubed in the numerator, I'm going to have an as squared plus a bs plus c. All right, and that's always the way it's going to break out. Now, so once again, the denominator gives me the basic building blocks of what the solution is going to look like. The numerator tells me how much of each of them I get. And the big question becomes, well, what about repeated roots? Okay. So say I have, the problem is if I do Ci is equal to s minus pi y of s, y of s, evaluated at s equals pi. So this is the normal cover-up, right? So the problem is, if I have repeated roots, then I'm still going to get a 0 in the denominator. This is still going to blow up to infinity. And therefore I have a problem. All right, so let's assume that y of s is going to be of the form some numerator of s, which I don't really care about, and I've got an s minus p cubed in the denominator. All right, so this is going to look like a C1 over s minus p plus a C2 over s minus p squared plus a C3 over s minus p cubed. And the problem is, so this one's easy. We know how to do that one. And that one's going to give me a C1 e to the minus pt. No problem. Okay. This one, however, is going to give me a C2 t e to the minus pt. And let's do that one is going to give me a C3 t squared over 2 factorial e to the minus pt type response. That's what I get with repeated roots. Okay, so the question is, how do I get C1, C2, and C3? I still have them. I still have the basic forms. I just need to find the mixing coefficients. So how am I going to do this? Can you guys see all the way down to the bottom there? In the back? I'm just noticing some craning heads. Well, there is a partial fraction, but there's essentially a trick to the cover-up method. Okay? And the trick to the cover-up method is the following. So C3 is going to be the easy one, and that's going to be s minus p cubed y of s evaluated at s equals p. Okay, so this is the easy one. So the last one in the chain is easy as can be. C2 is a little harder.
But Gabe, don't they all drop out though? If s equals p, doesn't s minus p goes to 0?
Correct, but it's in the denominator. S minus p in the denominator is a bad thing when I'm evaluating. That means I'm dividing by 0. That means the coefficients effectively blow up.
Right, but when you cross multiply all these things to get everything to equal.
Well, you could do it. You could do it as a cross multiplication, but now we're trying to do the cover-up method to get these guys for the repeated roots.
But those are that's the same thing, and don't the terms all drop out?
No, they don't. You actually wind up with zeros in the denominator that give you problems. You're going to wind up with effectively deficient equations if you do it. If you try to do it the cross multiplication method.
So that doesn't work.
That does not work.
Okay.
So the way you do it is, as I said, C3 is s minus p cubed times y of s evaluated at s equals p. That's the easy one. All right. I'm multiplying by all of them. Any ideas what we do with C2? Well, no, because 2 of them still leaves me a 0 in the denominator. So I'm going to bring out the dreaded. Okay, so I multiply it by s minus p cubed to get rid of it, right, and then take the derivative of the whole thing, and that gets me C2.
Why does that work?
What's that?
Why does that work?
The proof is in the book.
Okay.
You can look it up. It's and lastly for C1.
Is that S less than P or S equals P?
S equals to P. That's evaluate the whole expression at S equals P. And the last one is d2 ds squared of s minus p cubed y of s evaluated at s equals p. Right, so what you're doing is you keep doing higher and higher derivatives to keep going for every repeated root you have. So if you've got 2 repeated roots, you only need the first derivative. If you've got 20 repeated roots, you need the 20th derivative. But you keep multiplying by the full number. Right? In other words, you remove all of those repeated roots from the thing, and then you do it. All right. So the answer to all of this, or perhaps the question, is 1. So for y of t, maybe consistent. So given y of s, all right, to get to y of t is find the largest chunks you can in the table. All right, so you look up to the largest chunks, and what you cannot find, break up using partial fraction expansion. Okay, this is extremely important. All right, so the partial fraction expansion actually is kind of huge. It does tell you a lot of what's sort of going on, and again, it's the ability to see, and there's lots of sort of residue analysis and different ways to do this on sort of how to see it. But the main point is, I know how to do complex conjugates, and they always come in complex conjugate pairs. Okay, I know how to do repeated roots. I know how to do real non-repeated roots, which means that effectively I've got all the building blocks I need. Any idea how you do repeated complex conjugate roots?
Same way.
Same way as this. Okay, you just redo it. It's just nasty, but it's actually relatively simple. Complex algebra that you're going to go through. It's going to be, you got to keep track of what you're doing, or else you'll get it wrong. But it's straightforward. It's sort of, you put it in, turn the crank. After you've done it a couple of times and you trust your own ability to do so, then you bring out the sledgehammer, fire up MATLAB, and and do it in MATLAB. All right, which means you just write the equation down and say, I think residue, and it'll just spit out all the coefficients for all the different ones. And I'll break it up for you very nicely. Okay, so one of the things that we do that is actually on a question in the homework is the final value theorem, also known as FVT. Okay, and what this states is that the limit as t goes to infinity of y of t is going to equal to the limit as s goes to 0 of s y of s, with the big caveat, if and only if the system is stable, and by stable in this case, we mean that y of t, all right, is not going to infinity. All right? If it's unstable, then y of t is taking off towards infinity. You cannot apply the final value theorem unless the real part of every single pole is strictly less than or equal to 0. Right? And is it strictly less than? I think it might be strictly less than.
Marginally stable?
Well, the problem comes with repeated roots on the real. So I think in this case, this is only true if the real part of pi is less than 0. All right? That's the only way it works. Okay. Now,
This is why known as y of t in this question,
right, this is y of t. That should be a little y of t, right? If it's not, if little y of t is going, if it's unstable, little y of t is going towards infinity. And the interesting thing is the final value theorem will give you a value, by the way, perfectly happily. It's just the wrong one, because it only applies if the system is entirely stable. So, how do I check if a system is stable? Well, there's a couple of things. I can look again at my complex plane. So here's the real, and here's the j omega axis. So, if I've got a pole, remember that s minus pi, all right, or this c1 over s minus pi, is going to give me some c1 e to the minus pi t response, right? So anywhere, so I get this one, I get some decaying response like that. Out here, it decays a lot faster, right? Because this one is faster than that one, all right? Likewise, as I break away from the real axis and go up the j omega axis, what I get is this same decay as an envelope and then an oscillation inside it. Now, the place life gets interesting is on this one, I get an e to the plus t, e to the plus p1t response, right? Which means that this is actually growing exponentially without bound. And if I'm doing this one here, this one grows even faster, right? Because it's an e to the bigger t, right? Which makes it go exponentially faster. Likewise, if I break off the j omega break off the real axis to the j omega, I'm going to get the same envelope and an oscillation in between.
Question?
Yeah.
Oh, I was going to say, isn't it Q1 over S plus Q1 for the,
Done. Okay? So, where we consider stable is anything in that direction. The reason the j omega axis is a little interesting is if I have a single pole on the j omega axis, okay, that's going to be, if it's right at the origin, that's going to be a step, okay, which, if you think about it, is a sine wave with a frequency of 0, or rather cosine wave with a frequency of 0, all right, which means it's going to go to its initial value and it's never going to change. Okay, so that's a step. That's my my original one. The problem with this is that works, right? A single step is fine. Even if I have a single pair up here, these are going to be a pure oscillation, which does satisfy the bounded input, bounded output stability criteria. If I give it a bounded input, it's going to give me a bounded output. The problem is, what happens when I get a second pole right on top of the first one? So now I've got two poles on the j omega axis. Anyone? What's the response to the two?
It's unstable, but I don't know why.
It is not going to be exponential. Okay, this is, if we look just at this one, this is a 1 over s squared. Okay? What does a 1 over s squared response look like in the time domain?
T.
What's that?
T.
T.
The ramp.
It's the ramp. Right? It's going up linearly in time, not exponentially. Okay? So the problem is, anywhere that you have repeated poles on the j omega axis, you have an unstable response. It's going to infinity. Right? The problem is that you have to be very careful. So everywhere to the left of the j omega axis, and by the way, there's some really, really terrible jokes about this. Control system humor is not good. A tier 1?
Let's hear the worst one you know.
Oh, the worst one I know. If I have time at the end of the class, I'll give you the worst one I know. How's that? But the problem why the j omega axis is here, if I am just to the left of the j omega axis, and I've got two repeated poles on top of it, it doesn't matter, because that's going to be a t e to the minus P1t response, but the exponential goes down faster than the linear goes up. And therefore, that's always going to decay towards 0. Right? Even if I'm right just to the left on the very, very inside, it's still going to go faster.
You can't be on it.
You can't be on the j omega axis. You've got to be inside it. It has to be a negative real part. Okay? But e to the minus anything t goes to 0 faster than t increases, or t squared, or t cubed, or anything above. All right? That's the whole point. It's an exponential, always goes faster than any power. All right? So everything in here, even with repeated roots, is fine. The j omega axis with singular roots is okay, but the j omega axis with multiple roots is not okay. So generally we sort of punt and we say anything on the j omega axis, the usual term is it's marginally stable, but really you have to be very careful on your definition, but the way we use it, we consider the j omega axis to be unstable. Right? So everything to the left is okay. Even if it's just a smidgen to the left, it's okay. I can still apply the final value theorem. Okay. Now, in general, we get a sort of a close cousin of the final value theorem is what is called the DC gain. Okay? The DC gain of the system means essentially, so in general, this is some complex number. And remember that for a linear system, if I inject a sine wave in to my plant, I will get a sine wave out at the same frequency. Right? So if I have omega t going in, I'm going to have omega t going out. It's going to be offset by some phase, and it's going to be changed by some amplitude. Right? So basically the amplitude and the phase change, but the frequency of the sine wave does not change.
And that's the DC gain, right? The amplitude and phase.
The amplitude and phase are not the DC gain. The amplitude and phase with omega equals 0 is the DC gain. Because that's the definition of DC. Right? Is that there is no frequency constant. Okay? So when omega equals 0, then yes, then the amplitude that you get is the DC gain. It tells you sort of after everything is settled out, I want to know how much bigger or smaller is my output than my input was. So think about this for a second. If I take my it's time for a plant. Okay, so I take my plant and I'm going to inject some input u of t into it, and I'm going to find out what's going to come out. So if I inject a step into this, and I let everything settle out till it's all quiet, and I say, okay, I put in a step, I allow all the transients happen, and it calmed down, and I let it go all the way in time, and I say, okay, I put in a step, I got back 0.8. I'm going to say I have a DC gain of 0.8. So on the other hand, I got a value back of 2. So I have a DC gain of 2. All right. So in the Laplace domain, this looks like u of s is equal to, well, what's the step? The step is 1 over s. Right? I'm going to run this through, in the Laplace domain, my h of s. So I'm going to say that y of s is going to equal to h of s times u of s, which in this case, u of s is just 1 over s. So this is going to be h of s divided by s. But now what I really want to know is, given this input, I want to know what y goes to as time equals infinity. So now I apply the final value theorem. And I say the limit of y of t as t goes to infinity is equal to s, y of s, as s goes to 0. Right? That's the final value theorem. So now I've just got a special input that I put in. So this is now y of s, is h of s over s, right? So that's just going to be, for this one, that's just going to be equal to s, h of s, divided by s, evaluated at s equals 0. Those two cancel. So the DC gain of a system is equal to h of 0. Okay, so I'm going to take my transfer function, I'm going to evaluate it at s equals 0, and that's going to tell me what my DC gain is. Okay, with which caveat? It's got to be stable, right? Because if it isn't stable, I've applied, buried into this calculation of the DC gain, I have applied the final value theorem. Right? So therefore, I just got to be careful, right? Because the final value theorem only applies if the system is stable. Okay. Now, here's a dumb example. So, just whipping numbers out of the top of my head here. S squared 3s 16 over s cubed plus 7s squared plus 9s plus 32. And I want to know what the DC gain is. That's an h of s. Plug in 0. So what is it? 1/2, right? Boom.
Well, but you need to see it.
Aha. That's right. I do need to see what comes out. I have to check, all right, whether or not these are stable. Now we're gonna get to a different way of checking stability, all right. But one of the quick tricks that you can do is all the coefficients must be strictly positive and strictly, well, they'll have to be the same sign, okay? And zero does not count. So if any one of these is dropped, you immediately have an unstable system, right?
So if the 7s squared was missing?
So right, so if this was this, I immediately could tell you that that is not a stable system. That's an unstable system. Okay.
How can you tell that from there?
Because a necessary but not sufficient condition for all of the poles of the characteristic equation, the denominator being real, being negative real, is that all the coefficients must be strictly positive, which means none of them can be 0. They all
The squared coefficient there
is 0, and therefore it's not. Now, if they're all negative, that's okay. You just bring out the -1, and you're back to strictly positive again.
Now, can we say, if we put 7s squared back in, can we say it's stable?
You cannot. But what you can say is, but if it's not there, you guarantee it's unstable. Likewise, if this was a -9s squared, I guarantee you that's unstable. All right? Guaranteed. All right? I can't tell you if it's plus, if it is stable, but at least I know it's not. At least I know from a first glance that I've satisfied the necessary condition, not the sufficient one. Okay.
Gabe?
Yeah. We'll get to that a lot more.
If you're missing one of the coefficients, or it's a flip sign, that says that pole's in the right-hand plane?
No, we'll get to the root criteria, which tells you how many poles are in the right half plane. It just tells you, sort of as a shortcut, and believe me, you use this all the time. You do these hairy equations, you sort of go all the way down, and you balance, you get all the way to the end, and you look at the transfer function, which is this complicated gobbledygook in S, and you're like, ooh. Yeah. Basically, you all of a sudden say, uh-oh, this one's problematic. Right? Especially in electronic circuits, you can find yourself with a uncontrolled ringing that will saturate immediately. And if you haven't yet driven an op-amp unstable, raise your hand. You will. You've never driven one unstable?
He's scratching his head.
Yeah. Okay. I was going to be impressed. It's very easy to drive one unstable. The easiest way, by the way, to drive one unstable is to hook it up in positive feedback rather than negative. Which, since you have to sort of look on the pins to see which one is marked, that's a real easy way. Okay. So DC gain is simply h of 0. Now, here's the really neat thing. There's a reason I'm sort of hammering this home a lot. But the idea is that we can build up a huge amount of intuition.
Are you going to finish the stability? Are you still going into we discovered that, or we know that?
Oh, we'll get there a little bit later.
Okay.
But we will get there shortly.
You haven't proven stability for it yet.
No, we haven't proven stability. If anyone, Shell, do you have MATLAB fired up there?
No, you want me to do it?
Just find the roots of 17932.
Okay.
Just tell me whether it's stable or not.
That's root or?
Yeah, roots.
Wait, it will be stable.
Huh?
How do you know?
It might be stable.
How do you know?
We don't know that we don't know that it's immediately unstable, right? We don't know that it's.
Aren't all the roots going to be negative?
That's what I'm asking you. Just check.
Oh.
All the coefficients being strictly positive is a necessary condition, but it's not a sufficient condition.
Oh, really?
No, you have to do the Ruth criteria to find out whether it is or not.
Okay.
All right. So if any of these are negative, immediately 17932. Does your calculator do it?
Yeah, they're compliant.
Yeah, but are the real parts?
Yeah, they're all negative.
They're all negative. Okay, so this is stable, so this applies. Have you found out that one problem yet?
Yes.
And?
Almost.
Okay. Huh? Oh yeah.
Oh, that's why.
There's a lot of complex math that goes in that.
That's why you use the MATLAB.
Well,
Right.
Let's shoot it out. Then you
Yep.
verify it's matrix correct.
Yeah.
that's true.
Well, this is MATLAB.
Anyway, okay, so the idea is I can build up a huge amount of intuition about my system by inspection. Right? Once I factor the denominator, so look how far we've come. Take some system of differential equations, slam it through Laplace, which basically says take every ddt or every dot and replace it by s. Ignore the initial conditions because we always do things from fixed initial conditions anyway. Slam it through. All of a sudden, do a little algebraic manipulation, and we now have a transfer function. Factor that transfer function, which again is pretty trivial to do. And in fact, at least half of you have calculators that can do it. And all of a sudden, boom, I can now tell you what the response looks like. I can tell you about stability. I can tell you all kinds of things that are going on. Immediately, I'm starting to build up this huge amount of intuition. So what we are trying to do is where this is leading up. So the roots of the system, which we refer to as the poles, is leading us into what is referred to as the root locus design. So what we're going to be doing is we're going to be looking at how do we move those roots around. So we're going to take a look at our transfer function. We're going to see where those roots line up. And where those roots line up, we're going to say, I don't like where these roots line up. I'm going to move them somewhere else. I'm going to move them somewhere else where I'm happier with them. Okay? And we're going to learn some very powerful and very easy techniques to learn how to move the roots around. Yes?
So that means you can take an unstable system and make it?
Absolutely. Stabilizing unstable systems is the bread and butter of the control engineer. Okay? Now, the other problem is let me rephrase that. Stabilizing unstable systems is the bread and butter for which control engineers get hired. Destabilizing stabilizing systems is why they get fired. It turns out that feedback is a double-edged sword. All right, in that you can take an unstable system, you can stabilize it. You can take a system and move the roots around within certain limitations to where you want them and change the behavior. Now, again, there's some physical limitations. There are, for instance, they have a helicopter at NASA Ames that they have actually done an inversion of the plant, which is they have put a transfer function into the controller that looks like the denominator divided by the numerator. So what comes out of that is 1. All right? And then they put whatever dynamics they want to model into this thing, and they have a helicopter that they can make fly like just about any other helicopter they want to. All right? They say, you want to be, like a Gazelle, we can put it in a Gazelle. No, you want to be UH-50, we can make it behave like UH-50. You want to make it look like an Apache, we can make it look like an Apache.
You're talking about like the new, so I'm still two helicopters have specific...
So what they've done, this is called plant inversion. And in general, so here's a bad control system joke.
Oh, that's her.
We've already heard this.
Okay? So generally you say no plant inversion. All right? So this is...
What's the joke?
If you just see this sort of tacked up on a lab wall without any explanation of no plant inversion, people who have not taken a controls class will not get it.
Environmentalists will get pissed off.
They probably don't even know what you're talking about.
No, it's telling you not to.
What's that? The jury's still out. Okay. It's done, and?
Well, it turns out that if you go back to that.
Yep. No problem. We can go back here. Here we are.
Previous
Previous
one?
one. Oh, you want the one with the 2?
Yeah, the previous one. Go back.
You want this one?
Yeah, that y of t,
Yeah.
that 2a shouldn't be there.
This 2a should not be there.
Yeah, that's just a.
That's just a.
And the 2b is correct. So that's why you have 5 and 1 on your solution.
Got it. So this is there. So that 2 goes away then, right?
Yep. No, that's correct.
That is correct.
That's just the partial, right? Right.
Well, no, because if I'm gonna.
Okay, well, yeah.
So this 2 is gone. No?
Wait, how does that work?
Hmm? What's that?
No. I mean, the correct solution for A or.
So the correct solution here.
Go back.
So we had y of t here.
That's 5e
To minus 2t. Yeah, we got that.
And 2e to the minus t sine omega t.
Yeah, there is an e minus 2. Yeah, 2e to the minus t. That's right.
Sine.
Sine, okay.
Of 3.
So it does have a 2 there.
Yep.
Okay, so that's right. So then our formula here is correct, which is that we do use 2 times the magnitude of C1. Okay, which means I had an error in my notes and I put a 1 there. Okay, good. Nice to know. Excellent. Thank you.
Wait, could you go back a second?
Yes?
I don't try to the equation.
What's that?
Fired up now.
I'm going to try to the equation to make sure. Is that 62?
62. 5s squared, 16s, 62.
S plus 2 times.
S plus 2, hold on, we'll go up one. S plus 2 over s squared plus 2s plus 10.
2s plus 10.
Yeah, use convolution. CONV, s plus 2.
Will you
This
put
one?
it into MATLAB? Do you-
Not least the I inverse Laplace.
Convolution or?
Was that?
I can use inverse Laplace.
Okay.
When you put that into MATLAB, what command does it put that along?
So to put this in the MATLAB, I always do
Why does it come as opposed to small?
s plus 2 because you're convolving to do polynomial multiplication. Use the convolution command, CONV.
Okay.
So the way I would put this in, since we're doing that one,
Does symbol work?
you can do it symbolically, yes. But if you don't want to do it symbolically, so we had s plus 2 times s squared plus, what was it, 2s plus 10. Like that? So what I would type is cis equals transfer function of the numerator, which was, what was the numerator? S squared plus 16s plus 62?
Yeah.
Okay. So I would do 1, what's that?
5, right? Where's 5?
5s squared? Yeah, okay. All right, so what I would do is I'd do transfer function times 5, 16, 62, comma, convolution of 1, 2, for a 1 for the s, 2 for the thing, comma, 1, 2, 10. Okay, like that.
What is that going to do?
That is going to create an object in MATLAB that is this transfer function. And once you have that, you can do anything you want. You can do a step input, simulated, whatever you like. You can do an initial condition response. You can ask for the roots. You can do a root locus. You can do anything you want with it. Bodie plot, and once you have it there, once it is in MATLAB, you can do anything you want with it. All right, it'll give you just gobs of information about what to do with it.
Okay. And so what
Yeah.
was the solution you guys had?
The solution we had was 5e to the minus 2t.
Yeah, that's right.
That was easy. Plus 2e to the minus t sine 3t.
Sine 3t?
Yeah.
Yeah, that's right.
Yep. Okay. So yes. So good.
So you wrote cis equals transfer function?
Yeah. I wrote cis equals tf for transfer function. You can also do cis equals ss for state space. If you had a state space model, you can do cis equals zp for pole 0, or zpk for pole 0 gain, 0 pole gain, and just give it a list of zeros and poles. And MATLAB will switch between all of them to your heart's content.
And the convolution?
Yeah.
What is that?
That's doing the polynomial multiplication.
Okay.
right, that you have to do to get this. Right. You can also multiply it symbolically. So the other thing you can do is I believe you can do sys equals transfer function s with single quotes like that, and then you can actually type this in directly, just like a multiplication, and it'll have it. Yeah.
Can you see like the symbolic output?
Yeah, that's what this does.
Yeah, that's what I was talking about.
You can do it this way as well.
The output of comms is going to be all the coefficients.
Of the bigger exactly, the bigger one. It's a very, very useful one.
I mean, why does like this to write a token using symbolic like sim s, create a symbolic variable s?
Right.
And then just
I believe if you do sys equals tf and single quote s, it's the same thing as declaring s the symbolic one for transfer function.
Okay.
And then anything you type in s will be fine. Okay. So as I said, the roots of the system, or the poles of the system, is taking us towards a root locus design. Okay, and what I mentioned before was the class sort of bifurcates to two different design techniques: the root locus, which is all about the transient response, and also we go to Bodhi design. So I'm going to lead you up to, we'll take a little sort of detour here into Bodhi, and just because I want to sort of motivate this a little bit and show you what happens here. So if I take my linear system and I put in cosine omega t.
Did we get too off track for the health? You were talking about helicopters.
Oh, sorry. That was the, okay.
Why were they?
So what they do with the plant inversion is they do this. So you have some g of s as your plant. Okay? And what they do is they...
That's the denominator or numerator? Or
Right. That's in some that's in transfer function form. Okay? So you have g of s, which is your plant, which is your helicopter. It's your true dynamics of the helicopter, well-modeled, 60-second order differential equations, lots of coupled stuff. It's nasty.
And that's the one...
This is the real helicopter.
That's the one that Ames had.
Yes.
Okay.
And they've gone to enormous effort
To model it.
it. Okay, very carefully. That's how you get G of S.
Yeah.
This includes just all kinds of nastiness. Okay, and then what they do is they have a controller that has...
That's the inverted plant.
That's the inverted plant.
Right.
So what this looks like is K of S. Right? Because they cancel everything in the plant. This is called plant. Whatever they want to put in.
Okay.
All right? And so by having this 1 over G of S ahead of the G of S, what they wind up doing is canceling all the dynamics of the plant. Now, there are extreme limits to what you can do with this. All right? This is, as fast as the plant moves, you now have to have an actuator that can move faster in the opposite direction. All right? Because if the plant wants to go this way, you've got to push it the other way as fast as it does it to sort of wash out whatever the plant wants to do naturally.
But in words, it's like, it's totally amorphous. There's nothing to it. You're making it into whatever it is it can be whatever it wants.
So what you're doing with, the reason people do plant inversion is because they want to give it some desired set of dynamics. So you want to model some helicopter, for instance, which has not yet been built. And you want to see, how does this fly? All right? So you can do a couple of things. One, you can put in the equations of motion that you think the new one will have into a flight simulator and have the pilots fly it, see how they like it. Or, and they say, well, gee, that's great, but, you know, a flight sim's a little limited. So what they actually will wind up doing is put in the dynamics of what it is they want and wash out the dynamics of... Now, there are limits. You cannot take a Cessna 152 and make it act like an F-15. You can try, all right? And over, you know, really short transients, if you've got really big actuators, you know, you might get, you know... Yeah, well, you know, until you rip the thing apart, it'll, you know, for, you know, a tenth of a second, it'll behave like an F-15.
So you're saying like a big airplane with a smaller plane? I don't even know what you were...
So an F-15 is a very high-performance fighter, which can do things like...
No.
Huh?
The F-15, is that unstable?
Relaxed stability. I believe it's about 7% unstable.
The 22 is.
The 22 is very unstable.
Yes.
But I believe the F-15 is stable subsonically, slightly unstable supersonically, or vice versa. I can never remember which way the thing goes. Yeah, Shell.
Yeah, wouldn't you be like, isn't this like a very simplified diagram of what's happening? Because wouldn't you have to have like, loop around the feedback?
Oh, there's huge loops around the feedback. Yes, it's an incredibly simplified diagram. Okay, and they're measuring the hell out of the system. All right, and they've got this thing bristles with sensors and actuators. Right? I mean, they're all over the place, and there's a reason they do this, which is it allows them to do flight tests of things that don't exist. Right?
So I mean, in a simulator, you're also limited by how well you can model.
In a simulator, you're limited how well you can model, but the world behaves according to the simulator, so it's consistent. The problem with doing this is the real world does not necessarily behave the way. The real world doesn't care if you've actually perfectly matched these or not. If you've got a few things that, they're close, but they're not, you've actually created, what this is in a sense, when we'll get there later, is pole zero cancellation. So if you have your dynamics that look, if I plot the poles of the system, all right, so I've got, all of these various modes up here, what plant inversion does is it says, okay, I'm going to plop a 0 right on top of every one of these when you close the loop.
The zeros become poles.
So I'm just going to push, when I close the loop, I'm going to put a 0 on top of every one of these poles, and that means that the zeros are going to kill it. Right? Just as, so you have on one end going to infinity, on the other end going to 0, and the two of them looks like, 0. Right? I'm going to kill it, and then I'm going to replace it with some poles of whatever it is I'm trying to test. All right? And I'm going to try to determine whether these are good or not by flying the system. Now the problem is, and it's a subtle issue, but if I didn't get this quite right, but I put a pole, I put a 0 close to, but not right on top of the pole, I have actually created a mode in the system that I cannot control. Okay? My actuators, by putting that 0 there, any force that sort of tries to get there gets killed by the 0. Which means that this system has a runaway mode that I can't stop. I cannot control. In fact, I can't even see it.
Do they actually fly this thing?
Oh, yeah.
And it has actuators in it.
Oh, yeah, it's damn impressive. I mean, it is amazingly impressive what they can do with this thing.
I hope the test pilots have a really solid sense of fear.
No, actually, the test pilots have wonderful ejection seats.
Okay.
They have wonderful ejection seats that actually blow the rotor off before it punches them through the top.
I'm seeing a movie of this.
Well, that's what YouTube and Google Video are for. Yes.
So, is this a technique that's used a lot in modeling?
No, as I said.
This is scary.
Well, I mean, like.
No plant inversion.
Okay.
Okay, there's a reason. The only people who try to do plant inversion, let's see. There's a few cases where plant inversion is done. There are some model inversion control techniques. However, they tend to be of sort of like adaptive cancellation and things like that, which tend to be used in signal processing type environments. They rarely ever get done. Other than the sort of high-end sort of test planes, I can't think of a single physical, like non-electronic system that they've ever used plant inversion for. Can you think of one?
Well, no, the reason you typically don't is because you have minimum phase.
Yeah. And once you have a minimum phase.
Then it's non-negative.
So a minimum phase, by the way, means it's got a 0 out here, right? And just like you're putting a 0 on top of every pole, you're putting a pole on top of every 0. That one's unstable. So you now are pumping energy into the system. You have an unstable controller. So again, it will work. If you've got enough bandwidth on your actuator, it can be done. But as I said, of all the ones I know, they do it in things like active noise cancellation, things like that. I've never seen anyone other than sort of NASA or the like try to do one with a physical plant.
Yeah, well, I was kind of thinking of, like, there's a lot of audio things. Like
there's audio that's done, yes.
Music, instrument.
Although that actually
That
actually does not do, they actually don't use plant inversion for that, they use something else. They use a correlated input. And your question was?
Do they have models of this other company, small and big control?
Actually, I believe they test it tethered first. They actually have the thing on there's a lot of steps to go before they do this. Yeah, there's a lot of things they do where, they limit the ability to damage themselves before they do. They've been doing this for a long time. All right, and they've got, and they fly it in the simulator first, and they make sure everything, they've got a lot of very high fidelity models that do this. So the thing is, as I said, there are limitations. When you are doing things like this, you are making your actuators take an enormous amount of punishment. All right, and they are working very, very hard to try to undo what nature is trying to do, effectively. All right, and there are lots of things like that. So there was sort of
So in this block diagram,
Uh-huh.
KFS is just a pure control input.
KFS in this case is the model that you actually desire to track, and there is a feedback loop around here.
If it were the control input, then we'd have another box like behind GFS that's the new plant that you model.
Correct. That you would do.
You would do it after you did the inversion.
Generally, you would wind up that there's different ways, different places you put it, give you slightly different architectures. At this point, it's sort of not really relevant. It's something you guys are never going to do, so so don't get too excited about it.
How do you know that?
How do I know that? Do you see the sign? Do I need to make it bigger? So plant inversion, when it gets tried, is almost always, I've seen it in the case of outside of signal processing. The only time I've seen it tried is when generally people who are a little shaky on their controls, oftentimes people throw a machine learning or something at a control problem, and they sort of say, oh, this makes sense. I'll just invert all the dynamics and then run it through. Yeah, and life will be good, and it is for 0.3 of a second, and then it isn't. So this is the sort of the general place I've seen it. Okay.
In MATLAB, it always works, right?
Yes. You simulate it in MATLAB, it always works. That is absolutely a correct statement.
Isn't that subject to the precision of the numbers?
No, because in MATLAB it actually will hold the precision for you on both sides of it. Since you're giving it both the plant and the inverse, both are equivalent.
Yeah.
As far as I know. Okay. So.
Yeah, that was processing the Wiener filter.
By plan inversion, right? Wiener in signal processing they use plan inversion all the time. Right. Correct. And also the LMS algorithm that they use for adaptive noise cancellation can be related back to plant inversion. So there are a lot of neural network control algorithms that are fundamentally based on plant inversion. However, when you start getting sort of LMS, neural network, things like that, you're entering the realm of people who don't know controls, throwing whatever they think might work at it. You occasionally get this at conferences. You'll go and sort of, a lot of people will use PID, works great, and occasionally you'll get some oddball who's trying something, and you're like, what are you doing? And there's usually some really complicated wavelet functions of this and that they're shoving in, and you find out later they're a mathematician who's never done a control system in their life, and they're trying to sort of throw something they think will work.
Flying hammers.
Yeah, something like that. Okay. All right. So, getting back to our little excursion into Bodhi here. So I've got cosine omega t goes into my plant, and what comes out? Right? I've got an A cosine omega t plus phi. Okay? So for a linear system, if I shove an oscillatory term in, a pure oscillation in, I get a pure oscillation out with a difference in magnitude and a difference in phase. But what oscillates in oscillates out. It drives at the same frequency. All right, always. Okay, for a linear system. Now, let's say I do this. Okay, so I'm going to call it H of S for my plant, and I'm going to put in my U of S goes in, and U of S for cosine is S over S squared plus omega squared. Okay, and then I'm going to get out Y of S. Is this going to work? Anyone? Is this analysis going to work to get me back these values? How many yeses? Raise your hand. How many no's? Raise your hand. I got sort of 2.5 kind of no's. I got one strong no. All right? But everyone else is a little stumped. Is this going to, if I feed cosine omega t in, I'm looking for y of out, am I going to get a cosine omega t plus phi coming out? If I feed this cosine omega t, which is S over S squared plus omega squared, into H of S to do Y of S and do my inverse Laplace transform, am I going to get back the right terms? And they're going to find an easy way to find the magnitude and the phase.
Yeah.
So now, how many yeses? Hands, please. So I've got 1, 2, 3. I've got 6 of them. Are the rest no's? The rest really undecided? Okay.
Sheldon's been wrong on football, so he's probably going to run over.
Ooh.
I thought
Below the belt.
New England won. Wait, am I?
And we're talking NFL as opposed to...
So guys, keep down the chatter. So the answer is no, this is not going to work. But why is it not going to work? There's a subtle thing going on here. When I feed in U of S is this, I'm telling you that the system is quiet up to time t equals 0. And at time t equals 0, this goes to 1, and I inject my cosine omega t. Okay? Which means that my output of my system is going to do some transient response, and eventually it's going to start tracking cosine omega t. In the long term, you're going to get the right answer. But you're going to have to deal with this guy to begin. Okay? So so I can do this. I can use the final value theorem. Can I use the final value theorem?
Marginally, yes.
We're not sure. What do you
Right?
think stable system?
Is this, the whole thing, is that going to be stable? That's a pure oscillation. That is on the j omega axis.
Well, as long as there's only one root.
Yeah, well, this one, we can't apply for the final value theorem, we say strictly less than the j omega axis, not on.
Isn't it oscillating, so it's never really have final value?
Correct. Well, that's the problem with it. Right? So I can't use the final value theorem because it's oscillating forever, so I'm not ever going to reach a final value. Right? So this does not work. Okay? So there is a better way to do this. Now remember that the reason we're doing this is there's a complementary design procedures. On the one side, we've got root locus, okay, which is going to look for, things on the complex plane moving, coming together, and things like that. You're going to pick where you want to send. This is going to tell you, based on what kind of controller I put in, what kind of feedback, it's going to tell me where those roots are going to move as a function of the feedback. That's going to tell me one thing. On the other side of it, we have our frequency design, or Bodhi design, and Bodhi design is going to give me, I'm going to have something that looks like my gain and so this is going to be the magnitude of G, and this is going to be the angle of it, and this is going to tell me that some phase change. So by looking at these two, I'm able to actually do my control design the same way I am by looking at these. This one, complementary. So this is great for transient specs, and this is great for tracking specs. Okay, so transient tells me how fast does it rise, how much overshoot, does it ring, does it not. All of that's going to be answered here. There is some information contained for each other in each other side. Okay, but sort of keep this in mind. We're going to wind up going down this path first, the root locus path first. We'll come back to the Bodhi design towards the end of the class, but I want to sort of give you an idea. What's that? Okay, so let's do this. So we've already said this doesn't work because of these transients. Can't use final value theorem. So now I'm going to say, let me apply a little complex math. So I'm going to take my plant, I'm going to apply my cosine in, and I'm going to look for my cosine out. Okay, so this is cosine omega t, and I know this is going to come out a cosine omega t plus phi. Okay, so what I'm going to do is I'm going to say u of t is equal to a cosine omega t, which is equal to a over 2 e to the j omega t plus e to the minus j omega t. So this is just the complex representation of my system. Okay? And now I'm going to say that h of t, which is the impulse response of my system, of the plant. So now what I'm going to do is I'm actually going to run the convolution integral. Because, hey, that's how I do it. Right? We've sort of weaned you off of the convolution integral, but there's a couple of places where it's really damn useful. This is one of them. All right? So, and by the way, you guys have a homework for that asks you to do the convolution integral of, I think it's sine t times sine t. This is a fabulous way to do it if you're not going to use the tables. The table's the easier way to do it, but you know, if you want to sort of know how to do it both ways. So y of t is going to equal to the integral from, let's see, I'm going to call it from 0 to infinity of h of tau, u of tau, u of t minus tau, d tau. Okay? Where u of t is now equal to e to the st, where s is equal to plus or minus j omega.
What's the u above?
This one? U, a cosine omega t, which is a over 2 e to the j omega t, plus e to the minus j omega t, which is exactly this.
You just dropped the a over 2.
I just dropped the a over 2 because that pulls out to the outside. All right, so I'm going to drop the a over 2. All right, now I'm just going to do a generic solution using this. Well, this is going to be y of t is the integral from 0 to infinity of h of tau e to the s of t minus tau d tau, which is equal to the integral from 0 to infinity of h of tau e to the minus s tau e to the st d tau. Right, all I did was just multiply those out. Yeah.
The definition of convolution isn't a lower limit negative to it? Or is
Depends on whether you're doing the one-sided or two-sided. We're doing the one-sided right now. As you're going to see, we're going to play a little fast and loose with it, but it's okay.
So this one-sided, you can do the fast and loose?
Yeah. Well, no. I mean, the fact that we're choosing the one-sided versus the two-sided is okay because it doesn't. You'll see why in a second.
Okay.
This e to the st is not a function of tau. Therefore, I can yank that out of the integral. I can yank this out up to here. So for this, I now have e to the st, the integral from 0 to infinity of h of tau e to the minus s tau d tau. Does anybody recognize that's h of s, right? That equals to e to the st times h of s. Right? So now I'm going to wind up plugging back in for that one, and I'm going to say that this is then equal to y of t is equal to a over 2 h of s evaluated at s equals plus j omega e to the j omega t plus a over 2 h of s evaluated at s equals minus j omega e to the minus j omega t. All right, simple plug and chug.
So you're multiplying by e j omega t.
Yeah.
And e minus j omega t.
I'm just shoving it back through. So this is using my u as e to the st where s is plus or minus j omega, and just going through this whole thing right here. Works just fine, right? Because all I've done is just evaluated it at s equals j omega, right? E to the st, s equals j omega.
Okay, so what are you shoving that back into?
I'm just taking this result
Yeah.
for what the convolution integral looks like
Right.
and using it for s equals plus or minus j omega. That's all I'm doing. Right, and just showing you that there's two terms where s equals j omega in here.
I don't see what you're substituting in here.
I'm just substituting s equals j omega into this for the convolution integral. And you can see that I do it twice. Once for the positive j omega and once for the negative j omega. And that gets me back my cosine. And I have to put the a over 2 term back in. Since it's linear, the A over 2 just comes out the front.
So isn't e to the st times h of s equal to y of t?
Yes,
Okay, and then you're taking s and substituting it back in.
but it's only valid for s at plus or minus j omega. That's the integral we just did. All right. So now I've got this. So if I take h of s evaluated at s equals j omega, this is just a complex number. Okay? It's got a magnitude and it has a phase. All right? So the other thing I know is that the magnitude of h of j omega is equal to the magnitude of h of minus j omega. Right? So, let's see. The way to do this, let's say I have, if I have something, say it looks like this. So the magnitudes multiply and the phases add. So the magnitude in the numerators multiply to each other divided by the magnitude. So the magnitude of this evaluated s equals j omega is the magnitude of that one. So divided by, right? The magnitudes multiply, the phases add, right? So in this case, if I have, so if I substitute j omega in all of these, I'm going to wind up with, this is going to be equal to the square root of a squared plus omega squared times the square root of b squared plus omega squared divided by the square root of c squared plus omega squared multiplied by d squared plus omega squared. That's the magnitude. And then the phase of this guy is going to be arctangent of omega over a plus arctangent of omega over b minus the arctangent of omega over c minus the arctangent of omega over d. Right? So the phases add and subtract, the magnitudes multiply. Therefore, I can take this result up here, this guy, right? And I can say that, let's just look at h of s of j omega for a second. So h of s evaluated at s equals j omega is going to be equal to, in polar coordinates, me to the jc, right? And h of minus j omega is going to equal to me to the minus jc, right? So you're going to get plus or minus the phase, depending on whether you use the positive or negative j omega, and the magnitude is going to be the same for both. So if I put it all together, I'm going to take this, and I'm going to run it back in, and then compare that to my original cosine going in. I'm going to have that y is equal to ma times e to the j omega t plus phi plus e to the minus j omega t plus phi divided by 2, which is equal to m times a times cosine of omega t plus phi. So what this means is that when I take... Nope, because the 2 goes in to get back the cosine. Because cosine is this plus that over 2. So what that means is if I put in a cosine omega t here to my plant, let's call it h of s, and I get a cosine back out that's going to look like m cosine omega t plus phi, where m is equal to h, the magnitude of j omega, all right, and you can do this s equals plus or minus j omega, doesn't really matter, and phi is going to be equal to the angle of h of s evaluated at s equals j omega. All right, so this is actually going to form the basis of all of our Bodhi design, which is to say that I shove a cosine in, I get a cosine out with a magnitude that's the magnitude of the transfer function evaluated, by the way, along the j omega axis. This is where your Fourier transform comes back. This is nothing more than the Fourier transform of h, by the way, right, of your impulse response. And the angle, the phase lag that you get with it. Okay, so we'll stop there, and we will, I will see everybody in, yeah.
No office hours today, right, Gabe?
No office hours today, office hours tomorrow, 3 to 5.
M equals to...
H times j omega, H of S.
Over here, M is not that, right?
Yeah, it is, actually.
What, versus even j omega,
So when I take h of s evaluated s equals j omega, I've got m equals a polar coordinate of the magnitude times the phase response. So because of this evaluation is exactly the same, right? Which is h of s evaluated at s equals plus or minus j omega, m is the magnitude of it.
I don't get it still.
So you take h of s, your impulse response, okay, in the Laplace domain, and for s you shove in j omega. Okay, you evaluate the magnitude of it, which is just the, as I said, if it's a ratio of polynomials, it's just going to be the multiplication of the magnitudes of everything in the numerator divided by the multiplication of all the magnitudes of everything in the denominator. Okay, you're going to do that. It's going to be a ratio of two. It's just going to be a complex number. So h evaluated s equals j omega is a complex number. Okay, you take the magnitude of it, and that's the scaling factor for the cosine, and you take the phase of it, and that tells you the phase shift.
Yeah, but... Alright, I get that, but...
What's that?
Yeah, I know, we did, but...
I bet you didn't do it this way, though. This is a pretty slick way of doing it.
We did it quite hard.
Oh yeah, this is way slick.
The magnitude and the RPM same, but not
Right.
everything.
Right. Well, what this allows you to do is basically to prove to yourself that your cosine in gives you a cosine out, and that what's shifted is the magnitude and the phase shift.
Yeah, but see, the only thing confusing me here is if I just take it from this equation and solve for magnitude, my magnitude would be HSS divided by EJC.
No, EJC has a magnitude of 1.
Oh yeah, that's what.
Right. That was what was confusing you. So let me be a little bit more formal here and write this as S evaluated S equals plus or minus j omega.
Yeah.
Okay, and the thing is this is minus j omega here, right? The idea that the magnitude is the same, the phase flips, right? So if I take h here, and I've got h of s, and I evaluate it on what I'm going to do is I'm going to run up the j omega axis, and I'm going to evaluate what happens.
Yes.
At each point that I stop on the j omega axis, I'm going to have some complex number, right? So h of j omega is going to equal to some complex number. That number is going to have a magnitude, right, and a phase.
Exactly. Okay.
Okay?
Yeah.
And that's it.
Okay.
Okay? Let me, okay, why didn't it? Alright, this is, close that one. I just want to make sure I've saved the right one. I can do that one while this is